Welcome to part 6 of a lecture on designing organic syntheses. In the preceding lesson, we focused on 1,2 difunctional compounds, especially on amino alcohols. So in general, alcohol functionality, and one position further on, we had an amino group. Could be a primary, a secondary, or a tertiary amine. Means R's might be hydrogen or alkyl or aryl, or maybe acyl. So, might be other substituents attached. This is just the general structure. So, and there are various ways to get to this situation. Well, for instance, from the corresponding nitro compound, just by reduction, and then an acylation or alkylation or arylation. This is also possible, of course. So, and where does this derive from? Well, we need a carbonyl plus nitromethane or a nitroalkane. Under basic reaction conditions, we will observe, hopefully, the nitroaldol addition process. Alternatively, we could start from an amino acid and reduction with lithium aluminum hydride will deliver the corresponding amino 1,2 amino alcohol. Or we had examples where we made use of an epoxide as a reactive functional group, which then is treated with an amine. And an alpha bromo carbonyl compound, also treated with an amine, will give an alpha amino ketone or alpha amino aldehyde, which then subsequently might be reduced to the alcohol. So, that is then in 2 steps we get to a structure like that. Well, here in this case with an alpha bromo carbonyl compound, we also have already a 1,2 difunctionalized compound. So in general, let's have a look how to set up something like that. Okay, halogenation in alpha position of a carbonyl group. Of course, in this case, we would have to face a selectivity problem. How to distinguish between this and that side, of course. Well, and here, for instance, the disconnection we could plan at between these 2 carbons and rather simple. Let's take an acyl chloride on the one hand and an organometallic species on the other hand. And the acyl chloride then, as you know, has the advantage that we get relatively clean one-to-one reaction, whereas with an ester, for instance, the intermediate ketone is then generally more reactive against the reaction with an organometallic species than the starting ester. Then you preferentially have the 1-to-2 product. Another general scheme for setting up a situation like that, one could think about starting from an olefin, making use of a simple addition reaction to the olefin. Well, should be used to that if you imagine that this could be, for instance, an interhalogen compound, for instance. Of course, you would also have to face a selectivity problem in that case. How do you make sure that the X part ends up at this position and not at the other one? So, let's change to 1,3 difunctional compounds. A very simple but highly interesting example is this one. Let's start a retrosynthetic analysis in that case. Well, okay, we could disconnect here, and then we would have this oxygen with a donator functionality, this synthon. Well, sodium methanolate would be the compound that shows that reactivity of that synthon. But how do we get this one with an acceptor reactivity here? If we would have a leaving group and halide as a leaving group there, then this compound already would give a poly condensation product, of course, because you have that nucleophilic center within that molecule. The same result or similar result we would get if we make the disconnection here. Here, acceptor reactivity, and there, then the donator reactivity. Well, let's take ammonia. So, the synthetic equivalent could be something like that. But how do we get this terminal, this bromide, with the bromine sitting at the terminal carbon? Might not be that easy to get hands on. So there is a rather simple solution. Change the oxidation state. This is part of functional group interconversion, as we call it. So change oxidation state of that carbon let's take a nitrile, and by reduction we can get to the amino group. And now it's really easy because this derives from a conjugate addition reaction of methanol to that cyan acrylate. No, it's not this. It's acrylonitrile. Cyanoacrylate. Well, you know what cyanoacrylate is. That are compounds like that, specially used for glue. Okay. So this is the rather simple solution for setting up a 1,3-difunctional compound like that with an alcohol or an ethyl functionality and an amino group there. Other examples for 1,3-difunctional compounds. Very well known for you is, of course, this one. Well, deriving from the aldol addition reaction of this ketone and that aldehyde. If R prime has alpha acidic hydrogens, then of course you have a selectivity problem. This would become more reactive for the deprotonation and will be then the nucleophilic center, which will react with the carbonyl group with the higher carbonyl activity, and this is again the aldehyde. We already addressed that problem in the lecture about stoichiometric organometallics. An alternative is this one. With this SS ketal, this thioketal, and you remember that reactivity Umpolung involved in this retrosynthetic plan and of course in that synthetic step initially developed by Dieter Seebach. So that lithiated dithioketal could react with an epoxide and will of course give then after hydrolysis this intermediary product, and after treatment with mercury oxide, it's then possible to get to the ketone. Oh, okay. A 1,3 amino alcohol you might get also with involving a functional group interconversion, say a reduction of that ketone, and this could derive from the alpha-beta unsaturated ketone by conjugate addition reaction. So, and this obviously seems to be a aldol condensation product, but not necessarily. There are other methods to set up an alpha-beta unsaturated ketone like that. Well, for instance, some special Wittig type reactions, as you should know. A very nice method for also setting up those 1,3 amino alcohols, especially if you want to achieve that highly diastereo selectively, is by reducing such a heterocycle, which you can easily get as a racemate by a cycloaddition reaction of an olefin with a nitrile oxide. This is a nice example of a 1,3 dipolar cycloaddition reaction, also known as Hüsken cycloaddition. So the final step is just reduction, for instance, by sodium borohydride has sufficient reactivity for this simple transformation. One 4 difunctional compounds. Let's talk again about an amino alcohol, a 1,4 amino alcohol. You could get that in principle from that type of ketone, but be careful. This could give a condensation product. Like that. And here the idea is not only applying one functional group interconversion, but two. Also changing the oxidation state here. And then it's simple, a Michael type addition process, conjugate addition process under basic reaction conditions with nitromethane, corresponding carbon ion as a nucleophile. And I think hopefully it should be possible to directly reduce this to the amino alcohol without having to isolate those, and if a reduction is faster than that condensation process, you have good chances to get to that product. Here an interesting case where you have already two 1,4 relationships. 1, 2, 3, 4, and again 1, 2, 3, 4 here. Also an interesting idea to get to a structure like that, changing oxidation states of various positions. Let us get to a higher oxidation state here. And to a lower oxidation state here at this position. Since cis-trans isomerization might not be a big problem, we could think of this lactone as intermediate in our synthesis. And now this intermediate offers the idea to have methyl vinyl ketone as one starting component, and this moiety as a nucleophile means an ion here. So, and just write down tautomere like that. Okay, highly nucleophilic there, electrophilic here. Conjugate addition process. One more idea for setting up a 1,4 relationship between functional groups. Olefin plus dichloroketene. Dichloroketene is preferred because it's more easy accessible than the parent ketene. Just treating dichloroacetic acid chloride with an appropriate base. Some tertiary amines are mainly applied for cases like that, and I think we talked about that these ketenes tend to give a 2+2 cyclo addition product. Forming indeed cyclobutanones. You can get rid of the chlorides by reduction. And now, with the Baeyer-Williger oxidation, treating it with an pair acid, you will get to the lactone, and also a lactone like that has a 1,4 relationship between functional groups, this position and that position. 1, 2, 3, 4, of course. Okay, it's time to go to examples for 1,4 difunctional compounds. For one of the interesting examples, we need an allylic alcohol. And, well, you can get to an allylic alcohol from an aldehyde and a vinyl metal species, vinyl lithium or vinyl magnesium halide. An acylation of that allylic alcohol leads to this interesting compound, which enables you to perform an Ireland-Claisen rearrangement. So deprotonating here, maybe trapping it as a TMS ester enolate, and while already at rather moderate temperatures, that Claisen rearrangement will occur. Leading to this gamma delta unsaturated carboxylic acid with the base in the presence of iodine. You will then observe a iodo lactonization. So you have then a 1,4 relationship between those two positions and a 1,5 between this and that. Cycloaddition reactions, again, will also help for setting up 1,5 relationships. The first example, the Diels-Alder reaction with singlet oxygen as the dienophile. Leading to such a peroxide, and reduction will lead to this product. And now I notice that, well, we don't have 1,5 relationship in here, but exclusively 1,4 relationships. Okay? Let's see what the next examples will offer. Oh, again, another 1,4 relationship. Again, a cycloaddition process. With this nitroso olefin as a heterodiene and this olefin as a dienophile. So, and reduction of this heterocycle will reduce the imine functionality and the oxygen-nitrogen bond, since you've set that up as a cyclic system. The hydride will approach diastereo selectively, so presumably you will get a high diastereo selectivity and therefore stereoselectivity for that 1,4 relationship. So, and please take that example also down within the examples of 1,4 relationships. So, but finally, we will now see an example for really 1,4 difunctional compounds, and again a cycloaddition reaction, again a hetero-Diels-Alder process. So hetero-Diels-Alder reaction. Here we have an enol ether. Hydrolyze that enol ether. And you will get to that carbonyl compound with the OH group in delta position. So a 1,5 relationship, and you can of course also get to 1,5 diols simply by reduction. Finally, we should have a look at this target molecule as an exercise. Please try to figure out a route to synthesizing a structure like that. While looking for strategic bonds, certainly this carbon heteroatom bond is a strategic bond, since, well, very often carbon heteroatom bonds are strategic bonds, as we know, and especially this one. Since, of course, as a synthon, we would say, well, we should have a donator reactivity here, there, acceptor reactivity, and acceptor reactivity in beta position of a carbonyl group is a good idea, since alpha, beta unsaturated ketones exhibit acceptor reactivity in beta position. Yeah? So the first retrosynthesis step, therefore, is straightforward. Alcohol functionality here, there, that olefin, alpha beta unsaturated ketone. Okay. On the other hand, you can nicely set up alpha beta unsaturated ketones. We talked about that already today. Aldol condensation, or Wittig type, that Horner, Wadsworth, Ammons Wittig type reaction. So, now take it simple, that ketone and this functionalized furan as the second component. You might observe some difficulties since compounds like that have the tendency to form these hemiacetals, but in equilibrium. Well, then, as always, there are normally several ways to get to a target. Yeah? But one idea in this case would be, well, let's make the disconnection here. Having this epoxide as one component and for instance acetic acid, acetoacetic acid ester as the other component. You can nicely deprotonate here since it's double activated. Reacts as a nucleophile after hydrolysis, while ethanol is formed and it will decarboxylate as a beta-keto ester. So, and then you have set that up. You know. Could be a good idea. Well, one would have to make a literature survey about that epoxide. For sure, this will be very sensitive, since under the influence of Brønsted or Lewis acids, this epoxide will easily open up, since this carbocation is even more stabilized than a carbocation at the benzoic position, of course, because the furan is even more electron rich than a benzene ring. So I think this is enough for today. Tomorrow we will again have a look at 1N relationships, but especially for dicarbonyl compounds. So we will analyze the situation with 1,2 dicarbonyl compounds, then 1,3, 1,4, 1,5, and even how to set up 1,6 dicarbonyl compounds. Thank you for listening. See you tomorrow.